Hello everyone, I'm Yuede, assistant professor at the University of North Texas. In this presentation, I'm going to share our work, DEFInit, an automated system we developed to study the security posture of the Android Init subsystem. It identified more than 80 zero-day high-impact vulnerabilities in competitive Android devices. This work was done while I'm interning at Kryptowire in collaboration with Mohamed Elsabagh, Ryan Johnson, and Angelos Stavrou. Here is the booting process of Android. There are 6 major steps, starting from booting the ROM till starting the system server. Among them, the init process is a common process in Linux systems. It is the first user space process launched by the kernel and has high privileges. Different from Linux, the Android init acts as the system property store and supports init routines. The init routines include action and service. They are defined in resource files with extension RC, following the documented Android init language. This is an action example. It has a trigger with 2 system properties. The commands in the action body will be executed when property A equals 1 and property B equals 2. And this is a service example. It calls executable with optional modifiers. Android init routines can be customized by vendors, and only the system apps or processes can set system properties. Let's look at how Android init works in more detail. Android init and the routines are running with high privileges. Android allows system apps and init to exchange information by reading or writing system properties. Once the properties are written and the corresponding trigger condition is matched, Android init can execute an init routine at any point while the system is running. This allows a system app to easily perform high-privileged operations. The device vendors can configure and extend the behaviors of Android init by defining custom init routines. This would benefit vendors as they can leverage the init routines to easily adapt to the unique hardware features, diagnostics, docking, and mounting that cannot be done directly in a privileged app. However, if the system apps have improper access control, this can expose init routines to unprivileged apps, resulting in crossing security boundaries. As Android init is highly privileged, this would usually cause serious security issues. We have found numerous zero-day privilege escalation vulnerabilities due to custom init routines that are exposed to unprivileged apps. Let me show you a real example detected by our system. We assume an attacker-controlled third-party app has been installed on Android device. This attack app would broadcast a message. This message is received by a privileged system app that registered to receive that. Once received, the privileged app sets the system properties A to 1 and B to 2. These 2 system properties trigger the monitored init action. Later, this action will start a service named Wi-Fi test. This service will execute the referred script. Finally, the script would execute the setInforce0 command. This command disables SELinux, which disables primary system defenses, including access control enforcement between processes on the system. To find these vulnerabilities, we designed DEFInit, an automated system to identify exposed security-sensitive init routines, their behaviors, and the apps exposing them. We made the first study on the security impact of customized Android init routines. To this end, we have confirmed 89 high-impact zero-day vulnerabilities, including disabling SELinux, sniffing network traffic, reading system logs, recording screen, and others. In the following, I will discuss the details of the 5 steps shown in this figure. Given Android firmware, we first unpack it and extract init routine definitions. There are various challenges to do that. The firmware has multiple file formats. Init dynamically loads and processes RC files in the presence of extra sources of information, such as system properties preloaded at boot time. Init RC files can also import init sections defined in other files. The service and action definitions are polymorphic. For example, a service can override its parent definition by using an override modifier. To solve these challenges, we integrate a diversity of firmware file format unpackers. We start parsing at the root init rc file. Then we nest into the imported files in depth first order to mimic the dynamic behaviors of init. We also keep track of the merge or override options to handle the polymorphic definitions. The next step is collecting traces and estimating behaviors of init routines. There are two major challenges. The first one is how to estimate security relevant behavior of arbitrary programs. The second challenge is from the multiple formats of the program executed by init routines, including init commands, ELF binaries, and shell scripts. To solve these challenges, we first extract the program's code traces, including hard-coded parameter values. For ELF binaries, we collect static traces or called APIs on the control flow graph in a depth first order. For shell scripts, we developed a custom shell tracer to draw random to collect code traces. And this figure shows a simplified control flow graph. And we could collect the highlighted nodes as the code traces following a group of predefined security-sensitive commands and APIs. Then we would match the interesting trace sequences using static rules. For this example, it will match the rule of reading logcat logs. It tells us this program is highly likely to move system logs to SD card that can be further read by a third-party app. Next, we model the trigger conditions of init routines. The challenge here is the multiple interdependencies between init actions, services, Android commands, and APIs. For this example, the action requires two properties to be triggered. It will start service Wi-Fi test following arrow 3, which will execute the shell script afterwards. To capture these dependencies, we design a novel graph structure called init dependency graph, IDG. It is a directed heterogeneous graph. In IDG, nodes represent init triggers, services, and programs called by routines. Edges denote call edges between them, and conjunction relationships between conjects in composite property trigger. The previous example will be modeled like this. Using IDG, we can efficiently model the relationships between different objects. In the last step, we identify the exposed routines and their behaviors. This requires identifying app call sites that invoke APIs, setting system properties, and resolving the corresponding argument values. We also need to detect if a call site is exposed to unprivileged apps. To solve these challenges, we developed a context and a flow-sensitive property key and a value extraction technique. It can accurately identify the read or written property keys and the mapping between each property key and its corresponding value. We then identify the exposed routines by querying the reachability from IPC agent points to call sites on control flow graphs. We performed a large-scale study on 259 stock Android firmware images from 8 to 11, covering 21 top vendors worldwide. These images contained a total of 65,000 system apps with an average of 262 per firmware. Now let's look at the identified init routines. This chart shows the identified init routines per firmware based on Android versions. In summary, there are 223 init routines per firmware. 66% of them are custom. This shows the great extent to which vendors customize the init routines to introduce new functionalities. The chart on the right shows the exposed init routines per firmware. On the average, each firmware exposed 8 routines. 2 of them are security sensitive, and all of them are custom by the vendors. This chart shows the breakdown of the identified exposed behaviors grouped by behavior category. There are 515 exposed sensitive functionalities, which are from 430 unique init routines. They cover 173 unique apps, spanning 101 firmware from 13 vendors. We further manually inspected the routines to verify their potential security impact. This chart summarizes the outcome. So far, we have verified 89 vulnerabilities in 34 unique apps from 30 firmware of 6 vendors. We have developed and tested 59 proof of concepts. 3 vendors have confirmed our findings, covering 49 vulnerabilities in 11 firmware. Our disclosure process is still ongoing. The discovered vulnerabilities have high impact. Here we list some of the impacts, including disabling system-wide mandatory access control, executing arbitrary code with high privileges, spying on screen content and user activity, and others. So in conclusion, we systematically studied the security impact of Android init routines. We performed an automated and practical analysis. We have identified various high-impact 0 days in Android 8 to 11 devices. More details can be found in our paper regarding the routines exposed via the GUI, raw samples, vulnerability details, and others. Please feel free to contact us. Thank you for listening.